I'm going to talk about something completely different today. So I'm really glad to be talking at LUG, glad to be coming to LUG. Hopefully, in my talk today, even if you're 100% on premises, some of the concepts are useful and the information is helpful. So yesterday, at the beginning of my colleague Daryl's talk, he promised to juggle. However, he didn't end up juggling. Instead, he gave a tour de force demo of FSX for Lustre and a product that I work on, which is AWS Parallel Cluster. So what I am going to do today is I'm going to teach you something that is essentially a magic trick, and that's some aspects of infrastructure as code. So briefly, we're going to talk about what is infrastructure as code, talk about some key technologies, the difference between interactive and managed deployments, how infrastructure as code actually works, and finally get to actually how this applies to HPC. And then I'll walk you through a couple of brief use cases, and then hopefully we'll have some time for questions. So what is infrastructure as code? It's literally the opposite of racking and stacking, being down on your hands and knees in the data center, but I would argue that it's equally as fun. So essentially, it's the managing and provisioning of infrastructure through code instead of manual processes. What we have here, oh, you can't see that. Oh, it does work, sort of. So the general idea is that the practitioner, sysadmin, person in charge of IT, writes code. This is usually in a structured domain-specific language. Sometimes there are specific DSLs. Sometimes you write it in Python, JavaScript, Java, etc. That code is managed under source control because it's actual code. It can be pushed or pulled to a management server or an API. This either sits locally in the case of solutions like Terraform, or it is a managed service like AWS Cloud Formation. That API or management server declaratively manages the provisioning and lifecycle of all of the resources that you see over on the right. Anything that's defined in the code is managed by the automation server. So, some key technologies. You'll hear about these, maybe you read about them on Next Platform or whatever, some of you may be using them. We essentially have AWS Cloud Formation and AWS CDK. So Cloud Formation is a managed service for infrastructure as code. You write your infrastructure definitions in structured JSON or YAML, deploy it to the service. There's also an interactive infrastructure designer that some people like to use. It's at least nice for making interactive diagrams. CDK builds on CloudFormation, but lets you write your infrastructure definitions in the language of your choice as long as it's not Fortran. Terraform is a popular competitor to CloudFormation. Terraform is a local management server. So Terraform infrastructure definitions are written in HCL, which is a well-seasoned, nice, declarative domain-specific language. CDKTF builds on Terraform, but allows you to write Terraform definitions in the language of your choice, as long as it's not Fortran. Polemy is a more recent entry into the infrastructure as code space. It theoretically allows you to just write your infrastructure definitions using the language of your choice, including, guess what, not Fortran. And then we have tools that are somewhere in between pure infrastructure as code and things that a lot of us are probably more familiar with: Ansible, Chef, Puppet, Salt. These are technically configuration tools because they generally rely on some of the resources already being provisioned, and then you reach in and configure them with it. You can make these work for infrastructure as code if you need to. So a close analog, maybe running in your own data center, to CloudFormation is OpenStack Heat. So if anybody here is still running OpenStack and you've got Heat installed, it's a very close tie-in to CloudFormation. So how does this apply to HPC? So let's consider provisioning an FSx for Lustre resource in my AWS account. So when I first learn about a feature like FSx for Lustre or some other new service or capability, I'm going to go and I'm going to set up some examples there. I'm going to kick the tires, and I'm going to use the console, or I'm going to use a CLI. Here, we're essentially setting up a really fairly big, not big for this crowd, but a fairly big FSx for Lustre file system, nice throughput with inbound compression, etc. This is how you do it in the console. On the right is how you do it in the AWS CLI. You can see there's a tight mapping between the two. But if you reflect on Daryl's demonstration yesterday, Parallel Cluster handled a lot of the networking and security group setup for us that you actually need to wire a Lustre file system up with a cloud-based HPC. So what if you need to provision resources out of band and then connect it up to another resource? Well, it turns out that that ends up being a lot of button pushing and toggle switch flipping. And that's fun the first couple of times you do it, but realistically, you want to automate it after you've done it a few times. So this is where tools like CloudFormation, et cetera, come into play. So you declaratively specify your resources. Here, this is the same large, fast FSx for Lustre file system. On the left is how to define it in HashiCorp Terraform. On the right is how to define it in AWS CloudFormation. You can see that a lot of the values are similar to what we had, especially in the command line invocation. However, the infrastructure as code platform, CloudFormation or Terraform, handles the resource provisioning. But it doesn't stop there. It also handles making sure that those resources stay up and stay configured. It detects drift. If you need to make a change to the way that your file system, database, et cetera, is configured, you make a change to your code, push it into source code management, and it is, through whatever mechanism has been configured, picked up by the automation server and pushed into your production services. It's full lifecycle management. The resources are defined in the code. There aren't any surprises. So what does this kind of look like? So I'm trying not to throw up tons of JSON and YAML. A, it's really early in the morning. B, it's also utterly unreadable in PowerPoint. A lot of PowerPoint's generally unreadable. So what we're going to do instead is I'm going to walk you through a cartoon of a CloudFormation template. Now, don't tune out if you don't use AWS or this is new to you. Most infrastructure as code formats share these primitives. So in this diagram, this is a diagram of a CloudFormation template file. Essentially, a CloudFormation template deploys what we call in AWS a stack, and that's a collection of actual deployed resources. Each template has parameters, one or more resources, outputs, and it can also have mappings and conditionals to allow for lookups and conditional execution. Resources are the AWS and other types, the actual deployed components. These, by the way, can be other CloudFormation stacks, so you can begin to compose these things together. Resources have properties. Those are essentially variables for configuring the resource. Those can be either defined, you can hard code them, they can be defined up in the parameters, or they can be defined as the properties of other resources. And that's what's illustrated here. Outputs from your nested stacks can be used as parameters and property values for other dependent resources. When you deploy to CloudFormation, the service handles the order of execution, drift detection, etc. What you're essentially designing and describing here is a directed acyclic graph for your resources. You define what you want, how it all relates together. Then if you need to make a change, CloudFormation doesn't just blindly go in and make the change. It figures out how to least destructively do that. When you want to get rid of your stack resources, you delete the stack. You don't have to go in and one by one, click and delete each individual resource. CloudFormation then helps you ensure that there aren't any dangling resources, which of course can lead to, to persistent, lingering resource utilization and bills. So again, how does this apply to HPC? So let's revisit the process of standing up a cluster. So we're showing this in the context of Parallel Cluster UI because it's pretty, but it's just an editor and a manager for a configuration file. So you can also just write that file in an editor and deploy it using the Parallel Cluster CLI. And that's basically pcluster create, the name of your cluster, and the config file. If you need to update your cluster, it's pcluster update cluster, the name of the config file. Parallel Cluster is a great example of infrastructure as code. First, your HPC cluster is defined entirely as a declarative configuration file. Second of all, once that file is processed by the Parallel Cluster infrastructure, it deploys a cluster and everything that supports it into your AWS account. And behind the scenes, we use CloudFormation to accomplish all of that work. And in fact, you can see this for yourself. So this is what it looks like under the hood in the CloudFormation console. This is my LUG demo cluster that I just stood up. You can see that it's actually a CloudFormation stack. Here are all of the events that happened while that cluster was being stood up. Here are all of the resources that it generated. And that actually scrolls much farther than that. Here are the outputs that I defined, including like my publicly accessible IP, zones, the FSX file system that I created. There are actions that you can take, deleting, updating, etc. So what's the configuration file actually look like in Parallel Cluster? So your cluster definition maps your physical design, which is over here on the left. We know what this looks like. It maps this into a cluster deployed in AWS. And it's all pretty much in English, as long as your definition of English looks like YAML. So you've got your image. We want this to be a CentOS 7 box. Our head node has an instance type of X. It's deployed in this subnet. We use this. We want to use this SSH key. We define it for global SSH inbound access. For scheduling, we use the Slurm scheduler. We set some global settings for that. We define queues. We can create specific storage volumes on a queue basis. We can decide that we want to use the on-demand resource provisioning as opposed to the spot market. And of course, we define what types of instances we want in our queue. We can also define shared storage. Here we have an EBS volume mounted at /shared. We have a FSX for Lustre volume mounted at /Lustre. That in turn is tied to an S3 bucket implementing kind of long-term life cycle. So once your cluster is up and running, it's not just a static system. In addition to being able to mutate the various configuration options using CloudFormation, the cluster itself can dynamically scale according to the behavior that we've declared programmatically. We've said anywhere between 0 and let's say 64 nodes. When your cluster comes up, there are no compute nodes allocated. The head nodes sit there and wait. When you submit jobs, enough instances up to your maximum configured are allocated. But if that's not if you haven't hit your entire headroom and there's additional back pressure in the queue, more instances get spun up. As the job pressure goes down, the instances go down. And interestingly, and a lot of our customers do this, you can actually delete the entire cluster when you're done, with high confidence that you can bring it back up at a future state. So, returning to infrastructure as code. So this single file approach that I've been showing you works really well with customer-side management tools. It works well for use cases a lot of the times. But we've been hearing a lot of customer asks that say that they want more customizability. They want really even more integrations with complex IT environments, like their own Active Directory, stuff like that, other computing platforms, more automatability. So in Parallel Cluster 3.6, which is coming out in just a couple of weeks, we don't usually do this, but it's definitely in late stage beta testing now. We'll actually not just use CloudFormation on the back end, but you'll be able to use CloudFormation to actually drive your parallel cluster deployments. What that means is no more local client, pCluster CLI, no more web UI. You can simply embed these in your own processes. You can define everything in your cloud infrastructure, not just the core HPC infrastructure, in a standard template language. This also, by the way, should work with AWS CDK. We haven't tried it yet. I haven't tried it yet. But again, it would be really cool to define it in a common programming language, not Fortran. So, what's it look like to define one of these clusters in CloudFormation? So sorry, this is a little dark. If I'd known, I probably would have done not night mode, but I'm also allergic to light mode. So anyway, what we have is a CloudFormation template for a Parallel Cluster 3.6 cluster, where we also provision a virtual private cloud, basically a VPC, and a public and private subnet, and then we deploy that cluster into the we deploy the cluster head node into the public subnet, and the compute nodes into the private subnet. Essentially, you have a simple parameter set, the availability zone, the SSH key name, the max number of instances. Then we do the provisioning, and we do the cluster, and then we provision the cluster into those subnets. We don't have to specify the order of operations. We simply declare this in our file. To deploy this, you can still use the AWS CLI, but now it's a standard thing rather than the pCluster tool, and now it's just AWS CloudFormation create stack, or you can also embed it in any number of other things. You could use the Boto library, literally whatever you need to do. So why would you want to do this? So a couple of examples. One is kind of more theoretical, but it's based on real experience, from my previous life, and another based on a real customer story. So let's do a thought experiment. So you're supporting a team, and they have a really tight design, build, test, learning cycle. They're working on multiple problems. Maybe they're developing a pipeline of products. They've got really heterogeneous computing needs. So they've got data collection, maybe using IoT. They need to do ETL on data, plus maybe some QC jobs on modeling and simulation outputs. But they're also doing model training and inference, exploratory analysis, data visualization. It's a real challenge to fit all of these things together. So it's not that you don't know how to solve these individual things themselves, but trying to stuff them into a single computing paradigm. Do we make it all run in the cluster? Do we make it all run on Kubernetes? Do we use AWS Batch? Or can we integrate multiple paradigms together? Well, I would argue number two is a little bit more attractive. And this is the kind of architecture that you can really easily do, especially if you're familiar with infrastructure as code. Because you can build this out you can build this out incrementally. So since Batch on the left, EKS, which is Amazon's Elastic Kubernetes service, on the right, and Parallel Cluster are all directly usable with CloudFormation in a couple of weeks, plus FSx, plus S3, plus everything else in the Amazon cloud, you could build something architecturally that looks like this. And what you're seeing here is that you could handle your rote ETL jobs using AWS Batch. You could handle your modeling and simulation using Parallel Cluster with an auto-scaling queue. You could handle persistent services like Jupyter Lab, model servers, et cetera, using EKS, but they can all have a common file system, an FSx for Lustre store, one or more, connected with a high-performance fabric in the AWS data centers, and even these can be wired up with a data repository association to an Amazon S3 bucket, so you can also have long-term data archiving and presentation, or preservation. So this is still a lot of work to build something like this. But it would be even more work if you're doing it by hand and had to, kind of restart, from scratch every time you wanted to change something. With infrastructure as code, it's tractable, it's debuggable, and it's reproducible. So another example, ephemeral clusters, or as I like to call them, HPC ops. So I'm coining this right here. I didn't see it on Google anywhere, but I think it's an emergent computing paradigm that's made really easy with infrastructure as code. So we have a customer, Maxar. Their main deliverable is their weather forecast. So essentially, their objective is to beat the NOAA forecast. And then their subscribers essentially pay for that early access to a high confidence forecast. So there's a case study available at this QR code that talks about this, but essentially they beat the NOAA forecast by almost an hour using AWS. But what's really cool about the way that they do this is that their cluster, which is a relatively, it's a relatively sizable cluster, is A, exactly right size to their job. B, is entirely ephemeral. So it takes them about 42 minutes to run their forecast. They incur charges at AWS for about 45 minutes. And that's just a little bit of overhead for setting their cluster up and tearing it down. Other than that, they essentially have next to no spend for at least for this part of their business. And this is really cool. So each forecasting job is run on an ephemeral cluster. Sorry. Anyway, what's really interesting is that this was done before the CloudFormation support landed in Parallel Cluster. I suspect, I can't speak for them, although I do actually speak to them, but that they'll be really thrilled to see this, because this will probably represent a substantial efficiency in the way that they're implementing some of their HPC developer operations. So to conclude, infrastructure as code is a really powerful approach. You can use it for modeling and managing complex resource deployments. AWS Parallel Cluster, which is a cluster management tool, uses infrastructure as code to deploy and manage dynamic auto-scaling HPC. Parallel Cluster 3.6, out soon, will support cluster deployment directly using CloudFormation. This allows for more sophisticated integrations of your IT or complex IT environments and HPC, as opposed to having them kind of more walled off. It makes it a lot easier to implement DevOps, MLOps, Data Ops, HPC Ops, whatever you want to call it. So with that, I'm glad to stop, take questions. There's also some supplementary resources. If you want to learn more about any of the things that I've talked about today, we have workshops where you can actually work through, standing up your own cluster, working with FSx, working with Batch. We also maintain an active blog channel, a very entertaining YouTube channel, and we have a new community site launched at Supercomputing this year. which is still in its infancy, but also has a growing amount of information. So thank you.
Thank you very much, Matt. Do we have any questions?
Looks like we've
So a little bit late, but I was going to ask, you mentioned the elastic fabric adapter. Are you planning to do any kind of like a dedicated Lustre L&D for that? I probably should have asked this yesterday, but do you know anything about that?
Daryl, are you here?
Yeah, I'm here. Yeah, right
Thank
now
you.
we can't comment on what we're adding to. Sorry.
Yeah, right now we can't comment on what we're adding to the FSX for Lustre service in terms of additional networking capability, but we can talk to you privately if that works.
So we've seen some code on the screen today. Do you feel that this source of code, this style of code, is going to outlive Fortran?
Is it going to translate to Fortran? Outlive Fortran? Nothing will outlive Fortran. You're not going to. I'm not walking into that. Nothing will outlive Fortran.
Any other questions?
If we have no other questions,
Thank
I'd like
you.
to once again thank Matt Vaughn of AWS